So we should start with some advice. So I've put down 3 pieces of advice. So the first thing is do lots of problems. And the reason you want to do lots of problems is it helps you figure out what's going on. And because the exam is full of problems. There are 7 problems on the exam. And the more problems that you do, the more you'll be able to recognize other problems. You'll notice that the word is do lots of problems, not just like stare at lots of problems or put lots of problems on your pillow at night in the hope that by osmosis it'll go into your mind. But you actually have to engage with mathematics. The second thing is take care of your health. So we have people who do all-night study sessions for 2 or 3 days going up to the exam, and then they'll fall asleep during the exam. It's a very bold strategy, but I don't recommend it. I don't recommend it. So, get enough sleep. Get out and take a walk every now and then. Don't just sit down for 6 hours. You want to walk into the exam refreshed, your mind ready to engage. You don't want to walk into the exam when your mind is its most exhausted from studying. And when I talk about health, I also include mental health. Do not overstress yourself on the exam. This is an exam, yes, but if you've been putting in the time and the effort up to this point in the class, you should not feel very stressed. The exam should be not a huge obstacle for you. Now, the last point is pay attention to the details. This exam coming up is not technically demanding in the sense we're going to give you some crazy algebra that you've never seen or, factoring a cubic. There's nothing like that. But I will tell you that when we were talking yesterday about the exam, we were like, this is a common thing I see the students do. Let's put it on the exam and let's see if they're going to catch it. If you pay attention to the details, you're going to be fine. But if you just skim a problem and be like, okay, knee-jerk reaction, this is what I do, you're going to get things wrong. Read a problem and make sure you understand it before you start the problem. It's amazing how many people try to answer a problem without understanding what the problem is. I say that as somebody who has been grading for the last couple of days exams from other calculus classes. And it's remarkable how the problem will explicitly state, this is this type of problem. And people are like, no, it's not. I'm going to do something completely different. Well, good luck. It's not going to go out well for you, my friend. Okay, so let us begin. We're going to go in order. Number 1, a limit problem. Find the limit as t goes to 0 of 1 over 4 cosine 5t minus 1 over 4 divided by t sine of 3t. Now, some of you might say, I know lots of stuff. I've had this calculus thing before. I'm a calculus pro. I know what tool I should be using. I'm going to pull out something fancy like Le Hopital. Oh. Now, some of you are like, what's a Le Hopital? Well, good for you, because you can only use tools that we've talked about so far. So don't be fancy and be like, I'm going to brush up on my tools that we haven't talked about. So our tools that we've talked about so far, well, so we have to check. Now, first thing you should always check with every limit before you do it is to say, do I even have to do anything? And the way you check it is you plug in 0. So we say, okay, well, let's see. Right now, if I plug in 0, cosine of 0 is 0 and sine of 0 is 0. So you get 1/4 minus 1/4 over 0 times 0, or 0 over 0. Now, 0 over 0 does not mean 1. What does 0 over 0 mean? More work. Good. You're paying attention. Great job. Okay. So that means really what's happening is we've got to get some sort of cancellation. But we notice that this has trig functions in there. So whenever you see trig functions involved in a limit, you're going to remember the following fact. The limit as stuff goes to 0. This is the technical language here. Of sine of stuff over stuff equals 1. The reason I say stuff, it doesn't have to be just x or y, whatever. It just has to match. So as long as the inside of what's in the sine matches with what's underneath, and it's going to 0, the result is 1. So this is going to be the key whenever you see a limit that involves trigonometry. So we've got to remember that. Okay, well, now we proceed. We say, okay, I don't like fractions within fractions, so let's get rid of fractions within fractions. We can do that by saying it's almost the same denominator, it's just a cosine 5t. So we're going to keep going. Limit as t goes to 0, and this would be 1 over 4 cosine of 5t minus cosine of 5t over 4 cosine of 5t all over t sine of 3t. And now, common denominator, that's good. So that's the limit as t goes to 0 of 1 minus cosine of 5t over 4 cosine of 5t. Now that's the upstairs. Then the downstairs I can say, oh, well, that's really like 1 over t sine of 3t. Okay. Now at this point we're like, okay, the cosine 5t, that's great. 1 minus cosine of 5t is still going to produce a 0. We still have our 0 over 0 problem. Now the problem is that 1 minus cosine of 5t does not look like sine. And so we're like, darn it, we really wanted a sine. So is there any way we can turn 1 minus cosine 5t into sine? I mean, we could just like cross it out and write sine, but then of course that's not the same problem. So we have to say, is there something legally we can do that would work? And in this case, we say, look, 1 minus cosine, all right, I'm going to have a tough time with that. But 1 minus cosine squared. Now, there we're cooking. Because 1 minus cosine squared is sine squared. So we say, okay, is there a way to make it 1 minus cosine squared? And the answer is yes. Using conjugation. So conjugation isn't just about getting rid of square roots. Conjugation is really, let's square stuff. So if there's ever a time, for example, a cosine becoming cosine squared, that's to our advantage because there's a nice trig identity. So now we have a lot of stuff. Let's see what we have. So we have a limit as t goes to 0 upstairs, 1 minus cosine squared of 5t. And then downstairs we have 4 cosine of 5t times t sine of 3t. And then times 1 plus cosine of 5t. Notice downstairs I'm not multiplying that 1 plus cosine 5t through. You only multiply through the conjugate in the part that it helps, and that's the upstairs part. Now we can update the upstairs. So 1 minus cosine squared of 5t, I can cross it out. What does it become? Sine squared of 5t. All right, good. So at this point we're saying, I want to do this idea. So we have a bunch of sines. So there's a sine, in fact there's 2 of them upstairs. There's a sine downstairs as well. So I'm going to write this as a sine of 5t, and then I'm going to write divide it by 5t. And then I'm going to write another sine of 5t, and I'm going to divide it by 5t because that's what I'd like. That's what I'd like. I'd like to have sine of stuff over stuff. Now, the problem is, I can't just write stuff like that without somehow making sure I balance it out. So I'm going to balance it out by multiplying by 5t on each time. Okay? So certainly if I multiply by 5t and I divide by 5t, I've multiplied by 1. Life is good. Downstairs, well, let's see, we've got 4 cosine of 5t, and then we have t, and then we have this sine of 3t, and we're going to divide that by 3t, and similarly we're going to put a 3t up front. And then so we saw that 1 plus cosine of 5t. So I'm setting it up to help us get to the place where we can get nice things happening. Now let's make a note of a few things. We actually have some stuff that can cancel. There's a t that can cancel with a t downstairs, and there's another t that can cancel with another t downstairs. And now we're really close. I'm going to write it one more time before we get to our answer. Limit as t goes to 0. We have sine of 5t over 5t. And there's a sine of 5t over 5t. And then there's a 5 and a 5, which makes 25. And downstairs, what do we have? We have 4 times 3, which is 12, times cosine of 5t, which is the term there, and then times sine of 3t, divided by 3t, and then 1 plus cosine of 5t. All right, and now we're ready to go. We look at all our pieces. Sine of 5t over 5t, what does that do? It goes to 1. And that still goes to 1 if I ask the same question. Sine of 3t over 3t, what does that do? It goes to 1. Because again, what's inside the sine matches with what's underneath. How about cosine of 5t? T goes to 0, what does that go to? 1. And 1 plus cosine 5t as t goes to 0? 2, because it's 1 plus 1. And so what do we get? Well, we get our final answer is equal to upstairs 25 times 1 times 1, which is 25. Downstairs 12 times 1 times 1 times 2, which is 24. 25 over 24. And we're done. We're done. Now, let me just remark about one thing. Notice that as we were doing the problem, we kept writing the limit notation again and again and again until we got to the last step where we actually evaluated the limit. In that case, we didn't write it down. Now, the reason I'm pointing that out is we do take your notation into account. And so if you should be taking a limit and you don't write the word limit, you're going to lose a point. But if you've already taken the limit and you write the word limit, that's also wrong. You're going to lose a point. And our goal is, we don't want to lose any points. We want to get them all. Got to get them all. All right. Good. All right. Well, one down. So, number 2. And I couldn't fit this all on one, so there's another page that goes on. So suppose that f of x is as shown in the figure below. So this is a case where they're like, hey, look at this cool function. We're going to give it to you as a picture. So now you get to become somebody who gets to interpret pictures. All right. And we're going to ask a series of questions. And we say, okay, so for which values of a with -3 less than a less than 5, so in other words, in this picture, does the limit as x approaches a of f of x not exist? So we're asking the question, when does the limit not exist? So we sort of scan. We say, okay, it's looking pretty good, pretty good, pretty good, and then we see a problem. Okay, here there's a problem at 1 because we see that there's some sort of a jump in our function. As we come in from the left, it won't match what happens when we come in from the right. So we certainly know that 1 is a problem. Okay, and now we keep going. Looks pretty good. 3. Is that a problem for the limit? No. The limit exists at 3. Because as we come in from the left and come in from the right, we're still getting the same answer. So, not a problem at 3. And then we keep going, and that's it. All right. So the answer for part A is 1. Okay, so one of the things that we can look at from a picture is say, okay, when do limits exist? And then we'll do some more limits in a few minutes. So part B is related. Identify all discontinuities. And if any discontinuity is removable, indicate how the function should be redefined. Now, I should have added the phrase redefined to make it continuous, because you could just say, I don't know, let's make it 100. That's redefining the function. But all right. So where do we have problems? Where are we not continuous? Well, if the limit doesn't exist, that's definitely a discontinuity. So 1 is a discontinuity. Now, what type of discontinuity do we have?
Jump.
It's jump. It's a jump discontinuity. That's the kind of discontinuity where you your limit from the left and the right, they disagree. Okay, that's not removable. Any other place? 3. See, 3, the limit exists, and we can look at it and we say, the limit says the answer should be 2, but the function says, no, I want it to be -1. So this is a removable discontinuity. So anytime the limit exists, but the function isn't continuous, that's removable discontinuities. And if I can spell the word discontinuity. All right. Well, that's removable. So the question is that we need to figure out how should we redefine f of 3. So f of 3 really should be defined to be what? 2. And there's our answer. We didn't actually have to say what type of discontinuities they were, but, you know, we like to provide lots of information. Now, the next couple of questions are related. So, part C. What's the limit as x approaches 1 of f of x? Well, we've actually kind of answered that question. What is the limit as x approaches 1 of f of x? Does not exist. Okay, good. Well, hope they're all this easy on the exam. Limit as x approaches 1 of f of x. Well, if the limit as x approaches 1 of f of x does not exist, are we done? Do we even need to try? Well, we still have to check. We still have to check. Now, in particular, whenever you see a function which has a discontinuity, and really the reason here we have discontinuity is things aren't matching. So what we're going to do is we're going to do a quick check by saying, let's look at the limits from the 2 different directions. So limit as x approaches 1 from below of f of x, and then we're going to do the limit as x approaches 1 from above. But let's start with from below. So f of x. So the key thing here is this is sort of an onion problem. We have layers here. We're going to work through our layers. We know that currently x is approaching 1 from below. So as I approach 1 from below, what is the function doing? It's going to -2. So what I can do to help me understand is that saying, look, the innermost layer, I'm going to 1 from below. Now, the second layer, I could say, hey, that's the same as it going to -2. But from which direction? Can we actually say? So we're approaching -2. Are we approaching -2 from above or from below? From above. All right. Now, as we approach -2 from above, what does the function do? The function approaches that point. So we're going to the value 1. So I'm just sort of saying what happens at each layer. The innermost layer says, well, x goes to 1 from below. So I'm coming from 1 from below. Say, so f of x, my next layer, is approaching this value -2. And you can see I'm coming from the top side. I'm going down, so that means I'm coming from above. So I say now my next layer is going to -2 from above. What's it approaching? The answer is it's approaching 1. What about the limit as x approaches 1 from above of f of x? Well, again, work the onion. So the x is going to 1 from above. So I'm coming from this side. What's the function approaching? 1. From which side? From above, because I'm coming down into the value 1. So what's happening is then this is still approaching 1 from above. And so what is the function doing? Well, the function's still going to 1. Now we compare the two. Looking at these two, what do we see?
They don't equal, or they do equal.
They do equal. They're the same. So that tells us that the limit as x approaches 1 of f of x is equal to, whoops, almost off the screen there, 1. Okay, so there we go. There's part C. All right, part D, excuse me. Part E. Okay, f of x. All right, what do you think? What's going to happen? You might be thinking, well, if nothing else, we're going to be confused. No, that's not what's going to happen. We're just going to approach it in a similar way. So let's do some work up here. So we're doing a limit as x approaches 1, and we'll do it from both sides. So let's go from 1 from below of f of x. So I'm giving myself room so I can write notes underneath. So we know that right now this inside part is going to 1 from below. Now we say, okay, as you go from 1 from below, that is what we just did. That says you go to -2 from above. And now we plug that in and said, well, what is that doing? Well, that says we approach 1, but from which direction? So we're approaching 1 from which side? From below. You see, because we're going up towards 1. So we're below 1 as we go into it. So we're approaching 1 from below, and as f approaches 1 from below, what do we approach? So as we approach 1 from below, we approach -2. Now, so if we do f of x, as we say approach 1 from above, again working our layers, the inside part we know goes to 1 from above, but this is going to be really similar because we saw as soon as we approach 1 from above, then every layer after that we always approach 1 from above. So we approach 1 from above, we approach 1 from above, and so what's our answer? Our answer is going to be 1. So if we compare these two, what do we see? They're not equal. So the limit of f of x as we go to 1 is what? Does not exist. So it's possible that, depending upon how many compositions you have, maybe your limit exists, maybe it doesn't. It can turn on and off. It just is a matter of our function. And you can imagine that we can have much more complicated functions. Oh yes, we can. We can have more complicated functions. Next part. So we're up to part F. And I think we can see it. Find the limit as x approaches -2 of 1 over f of x minus 1. So, what happens? Well, the thing we should always think about doing here is we should always think about, okay, just plug it in. So, when we plug it in, what does the numerator become? 1. What does the denominator become? What's f of -2? Yeah, it's 1 minus 1. So we get 1 over 0. Now, when you see 1 over 0, what does that mean? Well, it depends on how we like to think of it. Now, more work is really 0 over 0. 1 over 0, you should think of it as I have a number, and limits are saying what's happening nearby. So I have a number near 1, in fact it turns out to be exactly 1 in this case, over a really teeny tiny number. So if you take 1 divided by a teeny tiny number, what are you getting? A huge number. So when you see like a 1 over 0, you should be thinking like, oh, this is blowing up. So this is blowing up in some sense. Now the question is, how is it blowing up? All right, so what does that mean? Well, we want to take a look at the values. So let's think about it. I want to look at f of x minus 1, and I want to look at it on both sides. So in other words, I want to look at it to the right and to the left. So let's look at it just to the right of -2. F of x minus 1, is that a positive or a negative value? So in other words, if you think about it, here's 1. If I look at f of x minus 1, am I below 1 or am I above 1? I'm below 1, so f of x minus 1 will be positive or negative. Just think of, like here's 0. Is 0 minus 1 negative? Yes. So here's 0.9999. Is 0.9999 minus 1 negative? Yeah. So what happens? Well, what can I say about the sign of f of x minus 1? It's negative when I'm around negative 2. So what's happening is I'm blowing up, yes. Am I blowing up consistently? Well, on both sides, I have 1 over a very small negative number, which means I'm consistently blowing up in the same direction. I'm approaching negative infinity. So this is an asymptote type thing, where when you look at it, what happens is it's going down in the same way. So this is a case when the limit is negative infinity. And so the key here, since I guess it says to justify, we probably say something along the lines of f of x minus 1 is negative near x equals negative 2. That would be the kind of justification that we would need. Now there's another question here, and oh, there's a typo. Let me fix that typo. This shouldn't be 5, this should be 4. Okay. Now you might be wondering, are we allowed to do that on the test? Can we just change the problems? No. No. You can't do that on the test. I'm a professional. All right. Okay, so limit as x approaches 4 of 1 over f of x minus 1. Now, notice this has the same issue because f of 4 is also 1. So I'm still having a division by 0 problem. So this is still going to 1 over 0. So the question is, what's happening here? So let's look on both sides. If I look on the, let's say, we'll start with the right. If I look at f of x minus 1, which is my denominator, am I positive or negative? I'm negative. What if I look to the left? F of x minus 1. Am I positive or negative? Positive. So what's happening here is, again, we have a situation where as we go to 4, 1 over f of x minus 1, it's really going to like a 1 over 0. But the issue now is that f of x minus 1 is positive to the left of 4, and f of x minus 1 is negative. Well, I probably should spell 2 with a T instead of an F. To the right of 4, which tells us that when we talk about what's happening at this function, we're having this type of behavior. It's going down from one side to negative infinity, and then it's going up to positive infinity from the other side. So what's happening to this limit? So the answer for that limit is the limit as x approaches 4 of 1 over f of x minus 1 is it does not exist because it's not consistent. It's going to different directions. All right. So our last problem, h. So for h, we'll go back to our picture in a second when we know what we need to read. So we have this function, g of x is f of x times f of x plus 2. And it says, find the tangent line to y equals g of x at x equals 0. Now, when you're looking for a tangent line, and in general, whenever you see the word line, you always say, okay, if I need a line, I need to find a point, and I need to find a slope. So our point, well, we know the coordinate for the x-coordinate is going to be 0. What would the y-coordinate be? Well, the y-coordinate would be g of 0. If we're looking for a tangent line to g of x, we would plug in whatever our x value is into our g function. What would our slope be? Well, the slope would be g prime is 0. So our slope is our number. All right. So that's what we're after. If I'm after a tangent line to y equals g of x at x equals 0, that's the information I need. Now, that has nothing to do with the let g of x equals f of x times f of x plus 2. This is just a standard information. So we're like, okay, so that's what we're after. So we say, all right, how do we find this? Well, g of 0, now I can say more about this part of the problem, what is g of x? Well, according to this, that's f of 0 times f of 2. So let's go back to our picture. We need to find f of 0, and we need to find f of 2. So we come back to our picture and say, okay, our function at 0 would be there. What value do you see? Negative 1. And our function at 2 is here. What is that? 1.5, 3 halves, 1.5. So f of 0 is negative 1. F of 2, I like 3 halves. So we get negative 3 halves. Now, g prime is 0. Well, if I'm going to do g prime is 0, I better start by saying what is g prime of x? Because I can't plug in g prime is 0 until I know what g prime of x is. What rule do we need to take the derivative of f of x times f of x plus 2? Product rule. And someone has said, and the chain rule, which is right. Because x plus 2, that's a function in a function. So, derivative of the first, that's f prime of x times the second, f of x plus 2, plus the first, f of x, times the derivative of the second. Chain rule comes in. So f prime of x plus 2 times the derivative of x plus 2, which is 1. So we need this at 0. G prime is 0. That's f prime at 0 times f of 2 plus f of 0 times f prime of 2. So we do know a couple of things. We already know that f of 2, for instance, is 3 halves. So we're going to have something times 3 halves plus, and we know that f of 0 is negative 1 times f prime of 2. So we need to know f prime is 0. Let's check. So we come to our picture. We say, all right, I need to know the derivative at 0. Now, the problem is, this looks like a big function. And we might say, I don't know how to take this whole function. But remember, when I'm talking about derivatives, I only care about nearby. So we focus our attention on the nearby. Nearby, what is my function? It's a line. The derivative of a line is the slope of the line. What's my slope of this line? Negative 1. So that says that f prime of 0 is negative 1. All right, f prime of 2. All right, back to the picture. Again, you don't have to focus on the whole function. Focus on the part near 2. And if we focus on the part near 2, we cover up the rest, we see a line. Well, what's the slope of that line? 1/2. Because we go up 1 over 2. 1 over 2. So f prime of 2 is 1/2. So we have minus 3 halves minus 1/2 gives us a slope of negative 2. So, updating our information, we know our point is at 0 comma minus 3 halves, and we know our slope is negative 2. So our line is y minus the y coordinate, y minus 3 halves, is equal to our slope, negative 2, times x minus our x coordinate, which is at 0. And we can rearrange this to say this is y is equal to negative 2x minus 3 halves.
For the exam, would we be able to just keep it?
Yeah, for the exam, one of the instructions, and of course, while you're sitting waiting for the exam, you have plenty of time to read the instructions. One of the instructions will say, you don't have to simplify unless explicitly told to simplify. And we very rarely explicitly say you must simplify. if you see a problem that says you must simplify, what that means is it's such a beautiful problem that it'll be a life-changing experience when you see the answer. And we want you to have that life-changing experience. So most of the time we will not tell you to simplify. As long as you have a form of an answer that is correct, we can take that answer. And we are very knowledgeable about what correct answers look like. All right. So be ready. Learn to read pictures. You can get lots of information from pictures. You can have discontinuity questions, limits questions, how do things blow up. You can talk about tangent lines because you can get things like flat lines, so you can find derivatives. So there's all sorts of questions we can ask you with pictures. So be ready in case we see a good picture problem. Okay, number 3. Using the limit definition of the derivative, find the derivative of f of x equals the square root of 1 plus 4 times the square root of x. Now, you might be saying, but there are so much better ways to take a derivative. We've learned better ways. And that is correct, but we still want to make sure you know the limit definition. It's an important thing to know. So I will say that when we put examples like this on the test, you might say, ooh, Steve, you've slipped. You've almost implied that there's going to be a question like this. I will tell you something now because we're friends here. I can tell you things. Historically speaking, 100% of exams in calculus class have a question of this nature. Now, might we break that 100%? This could be the time. However, 100% is a really good track record, and I would be shocked if this was the semester we broke it. So you should be ready for this type of question. Now, what is the limit definition of the derivative? In fact, there actually are 2 limit definitions, so this really should say using a limit definition, but that's okay. The one we'll probably use here is the one that's a little bit easier to manipulate. That's the limit as h goes to 0 of f of x plus h minus f of x all over h. So this is, when it says the limit definition of the derivative, this is a good one to go with. And I think we'll have another problem later on, and we'll do the other limit definition. There's 2 of them. You should know both of them. So I will say, even just writing this down usually gets you like 2 points out of 10. So even if you can't do any algebra, at least get 2 points. So, okay. But here we go. So we start. F prime of x, and again, I think it's a good rule, just write down the definition. F of x plus h minus f of x all over h. The following step is the step where more people lose points on this type of problem than any other step that's going to happen. Because in the following step, we have to tackle what is f of x plus h. And you might say, that doesn't sound so bad. Don't I just take my function, and wherever I see an x, don't I put x plus h? And the answer is yes, that's exactly what you do. And nothing else besides that. So just do it. Wherever you see an x, put an x plus h. Put parentheses, whatever it does, just make sure that you get that. Okay, so this is the limit as h goes to 0 of the square root of 1 plus 4. And now this is where I would normally write an x. I'm going to really put a parenthesis there just so I make sure I don't make any mistakes, of x plus h. Okay, I've safely navigated past the most dangerous part of this problem. I think we'll find out. All right, good. Now, here we start the fun. We know before we even do anything else this is going to 0 over 0 because the definition of the derivative always gets us 0 over 0. It's inevitable, which means that more work lies ahead for us. Because we have 0 over 0, here's our mentality going in. We're going to say, I want to cancel stuff off. In particular, I want to get rid of something that cancels with the h. So our goal coming into this problem is like, how can I get an h upstairs? How can I rewrite this in such a way that things work out nicely? So, looking at our problem that we have, What's something we can do to help us get to an h upstairs? Conjugate, yeah. This is just sort of like, you see a square root, you're thinking conjugate. You're thinking conjugate. All right. So, we're going to multiply conjugate 1 plus 4 square root of x plus h plus square root 1 plus 4 square root of x. Downstairs, we have the square root of 1 plus 4 square root of x plus h plus square root of 1 plus 4 square root of x. Okay. So, there we go. Off to the races. Equals the limit. H goes to 0. Now, the nice thing about the conjugates with square roots is you get rid of the square roots. Notice something, though. I, being a paranoid person, say, look, be careful. I'm putting parentheses here. Why? Because parentheses save points. So many people miss points, valuable points, because they forget small things. So I'll point out things that could happen. All right, plus this takes a while to write this one down. Now, in case you're wondering, is the one on the exam, if there is such a one, if there is such a one, would it be this complicated? Probably not. I like to put harder problems on the review. So if you're panicking like, I don't know if I can do one this complicated, you probably can do the one that we're going to see. Now, here's the reason I like parentheses. If you forgot to put your parentheses here, you might say, oh, minus 1 plus 4 root x, and you might forget that the minus goes to both terms, not just to the 1. And if you forget that, well, that'll lose you some points, because you're going to mess up your algebra later on. So you want to be careful. Use parentheses when you can. Now, you'll notice we still don't have an h upstairs to cancel. So you're like, conjugate again, right? That's what you're thinking, which is the correct thing. That's what you want to do. However, before we conjugate again, what should you do? Simplify. Someone used the word cancel, because what happens with the ones? They cancel out. You get 1 minus 1. Okay, so what do we really have? Well, we have the limit as h goes to 0. These, they both have a 4 in them, so we could factor that 4 out. 4 square root of x plus h minus square root of x. Whoops, I forgot a parenthesis downstairs. All right, over. And notice how I did not multiply through downstairs, because that would make life worse. Our goal is to make life better. Better living through calculus. So, what's our next step? Multiply the conjugate yet again. Woohoo! Conjugate. Conjugate. So, I forgot another parentheses there. All right, pay attention to your parentheses. Okay, so equals the limit. H goes to 0. Upstairs, what will we have? 4 times x plus h minus x. Over, downstairs, don't multiply things out. Just leave them alone. And yes, it gets a little bit messy sometimes, but that's okay. Things will get better soon. It gets better. Now, at this stage, let's think about things we can do. What are some things we can do? The x's will now cancel. Now, should you anticipate cancellation? 100% you should. If things aren't canceling upstairs, what does that mean? You've made a mistake. And go back and check your work. It's like a built-in, like you've lived a good life, things will cancel. If you haven't lived a good life, time to correct your mistakes. You know, and so okay, you should expect lots of cancellation. In fact, you should get to the point where everything in the numerator has an h. And in fact, what do we have? We have 4h. And remember, what did we say? We wanted to cancel an h. So what can we do now? We can cancel an h. And at this point, life is great. Because what do we see? We have a limit, and what's in our numerator? 4. And when you see a limit, and we just have a nice clean numerator like 4, that means it's game over, man. Game over. because we can take our limit now. Because we're not going to get a 0 over 0. All right, so let's take the limit. So I'm now taking the limit, which means I'm not going to write down limit anymore. But up until this point, I always write down limit. I have to keep writing it down. Notation, that's an important part. We talked about the numerator is 4. Downstairs, well, we have the square root of 1 plus 4 square root of x, because the h goes to 0. There should be no h's left in our expression. And then there's another square root of 1 plus 4 square root of x, so there's like 2 of those. So I'll have 2 square root 1 plus 4 square root of x. And then I have a square root of x plus a square root of x. Well, that's like 2 square root of x. And I can clean it up a little bit more, because 2 and 2 make 4. 4 divided by 4 would give 1. So 1 over the square root of 1 plus 4 square root of x times the square root of x. And that would be our answer. But really, the problem is not saying what's the derivative. The problem is the process. That's what's being tested. So do the process. Now, we being paranoid, wanting to make sure we get all our points, because we work hard. We deserve the points. How do we check our answer? Well, we may not check our process, but we can certainly check to see if this is the right derivative, because we know things. We know how to take this derivative without doing the limit definition. So we can actually do a really quick check. So if I were going to take the derivative of the square root of 1 plus 4 square root of x, first thing is I'd rewrite this in a calculus-like way. What's a calculus-like way mean? To the 1/2. There's no square roots. Because in calculus, we prefer the notation to the 1/2 power. So x to the 1/2 to the 1/2. Okay, so now we apply the chain rule. So we have 1/2, 1 plus 4x to the 1/2 to the minus 1/2. Is that it? No, got to keep going. Derivative of the inside. 1 goes away. Then we have the 4. Derivative of x to 1/2. 1/2 x to the negative 1/2. And we see, okay, 1/2 times 4 times 1/2 goes away. Then you see that 1 plus 4 x to 1/2 to negative 1/2, that's the term there. And x to negative 1/2, that's the term there. So, yep, it matches. It means we probably did something right. Good for us. Good for us. All right. Well, let's do another problem. Number 4. We should probably go faster, because right now you're probably thinking, we only get 75 minutes. We're not going at the right speed. These are longer problems. You'll be fine. You'll be fine. Like the one with 8 parts, we don't have any problem with 8 parts on there. We capped it, no more than 6 parts. I'm just kidding. There's not even 6 parts. Or is there? You'll find out on Thursday. Okay. Find the following derivatives. And so this is just sort of a know your rules. Know your rules. So when we talk about know your rules, you've got things like the quotient rule, you've got things like a product rule, and you've got things like a chain rule. Okay, so let's just work our way through. So the first one, what's the big rule comes into play on that one? Quotient rule. So, and then this cubed root of y, if we're writing this in calculus, what does this become? That's right, y to the 1/3. Because we're calculus people now. We write things in a calculus way. So, however you choose to remember, some people like to do low d high, less high d low. If it helps you remember, do it. If it doesn't, find a way that does. Okay, so we would take the bottom, so e to the 2y plus y to the 1/3 times the derivative of the top, 2y minus sine of y. Notice I should have mentioned this. Is there any problem with the fact that our variable here is called y? No. Look, variables can have all sorts of names. Just because we often think of y as a function of x doesn't mean we can make something a function of y. Okay, so bottom times root of the top minus the top, y squared plus cosine of y times the derivative of the bottom. Well, e to the 2y, what rule do you need? Chain rule. E to the 2y, and times it by a 2. And y to the 1/3, what's the derivative of that? 1/3 y to the negative 2/3. Good. All right, are we done? No, it keeps going. There's an over part. Divide that by e to the 2y plus y to the 1/3 squared. Square the denominator. Now, at this stage, what's the next step? Box it. Don't simplify. Believe me, we don't want to figure out whether you simplified correctly, because odds are pretty good you did not. So, just, if you get to a point where this is the correct answer, you're just like, fantastic, I'm not going any further. Life is good. We're staying there. Okay. Now, the next one. All right, the derivative of sine of x plus e to the x times tangent of 1/2 x squared plus x cubed e to the x squared. Okay, now, this is definitely an onion problem. There's layers within layers within layers. Now, the way you do this is you just work your way one layer at a time. Don't panic. You're going to be fine. All right, in order to have space, I'm going to put the answer down here. So we start with our outside layer. Derivative of sine. Cosine. What goes into cosine? Everything that's in there. Remember, the chain rule says take the derivative of the outside, but leave the inside pristine for now. Untouched, like a nature preserve of functions. X plus e to the x tangent of 1 over x squared. By the way, 1 over x squared, we probably should have rewritten that. What does 1 over x squared become? X negative 2 plus x cubed e to the x squared. All right, now it's just a matter of parentheses. Okay, so we've taken the derivative of the outside, plug the inside in. Next step says times it by the derivative of the inside. Okay, so we have x plus a lot of stuff. So the plus means it's a sum rule, so we have to take the derivative of both parts. Well, let's start with the x. Derivative of that? Oh, man, may all our derivatives be so good. Okay, e to the x times the tangent of stuff. What rule do you need? Product rule. So the derivative of the first, that's e to the x, and then times the second, tangent of x to negative 2, plus x cubed e to the x squared. All right, so the derivative of the first times the second, plus the first, e to the x, times the derivative of the second. So now I'm to the derivative of this tangent stuff. Derivative of tangent? Secant squared. It's one of the ones you need to know. It's on your list of things to know. What goes into that secant squared? Keep the stuff that was going to the tangent the same. X negative 2 plus x cubed e to the x squared. All right, are we done? No, we keep going because there's a chain rule here. Okay, now we need to times it by the derivative of the inside. All right, derivative of the inside. Derivative of x negative 2? Negative 2x to the negative 3. Plus, okay, derivative of x cubed e to the x squared. Product rule. Okay, derivative of x cubed? 3x squared. Then we multiply by e to the x squared plus x cubed e to the x squared. What rule do you need? Chain rule. Derivative of e to the x squared is e to the x squared times 2x. Okay, and then put in enough parentheses to finish it up. And that's it. That's pretty straightforward. It's just a matter of applying the rules. Keep track of where you're at in the process. If you sort of lose yourself, go back a step. What was I doing just before this? And you'll be fine. Okay. Part C. You have this notation, d squared d theta squared. What does this tell us? Second derivative. So, okay, so we know how to recognize when it says find a second derivative. So we're going to find the second derivative. So if we're going to find the second derivative, how should we start? Find the first derivative. Okay, so first thing is let's find the first derivative of this function, theta to the 5th, e to the 3 theta, and secant of 2 theta. Again, the fact that we have thetas, not a problem. Not a problem. Our variables can be anything. All right, so the first one, we'll speed this up a little bit. Product rule. So the derivative of the first is 5 theta to the 4th. Then we have e to the 3 theta. And then we add to that theta to the 5th times the derivative of e to the 3 theta, which is e to the 3 theta times 3. And I like to put the 3 in front. It just looks nicer. It doesn't have to be. Derivative of secant, we haven't done that yet. What's the derivative of secant? Secant tangent. So what do I plug into my secant? What do I plug into my tangent? Which one gets 2 theta? They both get 2 theta. They both get 2 theta. That's right. All right, are we done? We got times the derivative of 2 theta, right? Because we have to do a chain rule. Derivative of 2 theta? 2. Okay. Now, we said second derivative. That's just the first derivative. So find the second derivative, d squared d theta squared of theta to the 5th, e to the 3 theta plus secant 2 theta. Well, that would be the derivative of the first derivative. We'll just say that goes there. Okay. Which is a lot of stuff. All right. So again, I'll just try to do this quickly. The 5 derivative of theta to the 4th will give us 5 times 4, which is 20. Theta cubed e to the 3 theta. Then we're going to have 5 theta to the 4th, and then the derivative of e to the 3 theta. Well, that's going to bring down to 3, so that's 15 theta to the 4th, e to the 3 theta. Then if we come here, 3 derivative of theta to the 5th will be 5 theta to the 4th, so that's the 15 theta to the 4th, e to the 3 theta. And then 3 theta to the 5th times the derivative of e to the 3 theta. Well, that's going to bring another 3 down, so that gets us up to 9 theta to the 5th, e to the 3 theta. Then we come to the next part, derivative of plus 2 secant 2 theta tangent theta. Well, we're going to have 2. The derivative of secant 2 theta, that's secant 2 theta tangent 2 theta times 2 times tangent 2 theta. Whoa, I'm running out of space. Okay. Plus, all right, fun continues. Derivative of tangent, secant squared. So I'm going to have a secant squared. So first off, the secant 2 theta, that stays the same. Derivative of tangent is a secant squared of 2 theta, and then there's another 2. Now, if we wanted to, we could clean this up. Do you have to? No. But don't you just sometimes like to have like a nice, tidy answer? Yeah, sometimes you do. What's something you can do? Well, notice that these match, the theta to the 4th, e to the 3 theta. So there's really 30 of those. So 30 theta to the 4th, e to the 3 theta. Then there's 9 theta to the 5th, e to the 3 theta. And then here, on the end, we get 2 times 2, which is 4, secant of 2 theta. Then that's tangent squared of 2 theta. That's the part that you can't read over here. And then we get plus 4 secant cubed of 2 theta. And there's our second derivative. All right. Nice. Good. Okay. Number 5. If the average rate of change of f of x from x equals 1 to x equals 3 is 2, and the average rate of change of f of x squared from x equals 1 to x equals 3 is 20, determine the rate of change, and I should have said the average rate of change. Let me insert the word now here. Of f of x cubed from x equals 1 to x equals 3. Now you might think, oh, this can't be that hard, because if I want f of x cubed, it's just f of x times f of x squared. So is the answer 2 times 20? No, it's not going to be that easy, my friends. We're going to make it more fun. Let's find out what the answer really is. So when you see the words average rate of change, you should think of, there's a formula for that. So average rate of change, when you see that on a test, that means f of b minus f of a over b minus a. It's the change of your outputs over the change in your inputs. Now, by the way, the problem doesn't say it, but if you see the words instantaneous rate of change, what does that mean? That means the derivative. So here, that's not on our problem, but just in case you were to see it. Okay, so average rate of change. So whenever you see average rate of change, think of, here's my formula. So what we're going to do is we're going to translate a statement here into the formula. So the average rate of change of f of x from 1 to 3 is 2. The is an equal sign. The average rate of change from 1 to 3 means you plug in b equals 3, a equals 1. So f of 3 minus f of 1 over 3 minus 1, that's my average rate of change from 1 to 3, equals 2. Another way to write this is that f of 3 minus f of 1 would be equal to 4, because 3 minus 1 is 2, and 2 times 2 is 4. So that's the first sentence. We rewrite it in terms of the formula. I shouldn't say the first sentence, the first part of the sentence. The second part, the average rate of change of f of x squared from 1 to 3 is 20. So f of 3 squared minus f of 1 squared over 3 minus 1 equals 20. So I can again multiply both sides by 2. F of 3 squared minus f of 1 squared would be 40. Now, what I'd like to do is actually solve for what is f of 3 and f of 1. That would be great. Notice something here. F of 3 squared minus f of 1 squared. What do you have? Difference of squares. And if you have a difference of squares, you can factor a minus b times a plus b. So again, if you see a squared minus b squared, a minus b, a plus b. Do we know either of those two terms?
Yeah.
F of 3 minus f of 1 is 4. So f of 3 plus f of 1, what is that? 10. Because I can divide both sides by 4. Okay, so what do we have? At this point, we've got the two formulas. F of 3 minus f of 1 has to be 4. And f of 3 plus f of 1 has to be 10. Well, two equations and two unknowns, because the things we don't know are f of 3 and f of 1. So now you look for ways to combine. So there's lots of ways to combine. You can do things like substitution. I like to do addition. If I add these two things together, 2 times f of 3, the f of 1's cancel, equals 14. So what does that say about f of 3? F of 3 is 7. Now that I know f of 3 is 7, I get that 7 minus f of 1 has to equal 4. What does it say about f of 1? F of 1 is 3. So I've actually recovered what the value of the functions have to be at 1 and 3. Are we done? No. Because the problem said, hey, I want an average rate of change. So now we plug it into the formula. So that would be f of 3 cubed minus f at 1 cubed, because my function is the f of x cubed, and my locations are 1 and 3. I'm going to divide it by 3 minus 1. So that would be 7 cubed minus 3 cubed over 2. And could we leave our answer like that? Yeah, we could. But if you wanted to, of course, as we all know, 7 cubed is 343, and 3 cubed is 27. And if you take 343 and subtract 27, you get, that is correct, 316. And divide 316 by 2 gives us, right, 158. So that is also an acceptable answer. So someone did point out that I drew my arrows wrong for the answer for part G of number 2. So the correct arrows are that way. So I would have lost a point. Ah, well. But we drop a problem, right? So I'll still be okay. I just can't make another mistake. So if you see me make a mistake, you should say, Steve, you fool! I make mistakes. I make mistakes. Don't assume your teachers are infallible. All right. So the good news is we went through some of the longer problems. And, well, maybe. 7 is going to take us a while, but the rest of them are fairly straightforward and will go pretty quickly. So we should be done, hopefully, more or less on time. So number 6, find all the asymptotes for g of x. Now, all of them, yes. Not just some of them. We don't just want 1 or 2 asymptotes. Got to get them all. Okay, so how do you find asymptotes? Well, first off, you realize that there's 2 types of asymptotes. There's the horizontal variety, and then there's the vertical variety. And so you've got to make sure you account for both. So we're going to start with the horizontal. Now, when we talk about horizontal asymptotes, what we're talking about is what's happening as we head off to infinity. And there's actually 2 types of infinity. So let's handle those first. So, okay, we're going to look at what happens to our function. Say, let's go to negative infinity first, of our 2e to the 2x plus 3e to the x minus 5, and divided by e to the 2x minus 4e to the x plus 3. So what we do, the first thing you do whenever you have any limit at all, is you say, all right, let's plug in. Now, we don't plug in a negative infinity because that's not a number. So when we talk about plugging in at minus infinity, what we're really saying is, what happens? What's happening to these expressions? So for example, e to the x, let's just start with that. If I have e to a very large negative number, what's going on? It's getting close to 0. It's going towards 0. So e to a large negative number goes to 0. So the 3e to the x is going to go to 0. Swimming downstairs, negative 4e to the x goes to 0. How about the e to the 2x? Goes to 0. So in fact, this is a beautiful limit. We can just say, oh, it's 0 plus 0 minus 5 over 0 minus 0 plus 3. Or it's negative 5/3. We just have to plug in. So this is the kind of limit that we hope for. The kind where it's just plug it in. Let's look at the other side. So for the other side, take a limit as x goes to plus infinity. Well, we're going to have 2e to the 2x plus 3e to the x minus 5. Downstairs, e to the 2x minus 4e to the x plus 3. Well, what's happening to e to the x, or e to the 2x? What's that doing? Yeah, it's getting huge. So we have like infinity plus infinity and minus 5. And downstairs, infinity, minus infinity, and plus 3. I'll tell you, the minus 5 and the plus 3 are not very persuasive when sending up to infinity. So, essentially what you have is some sort of infinity over some sort of infinity. What does that mean? More work. Infinity over infinity is a more work type problem. Okay, so the problem is things are blowing up. They're getting out of control. So what do we need to do? We need to slow it down. Slow it down. So I like to say pump the brakes. Pump the brakes. We want to slow it down, and not just slow it down, but we want to slow it down by just the right amount. Now what's just the right amount? You say which one of these things is growing the fastest? So just pick a numerator or denominator and just say which one is the biggest? E to the 2x. That's the growth. That's what's causing it to get the biggest. So the way you slow it down is you say, all right, we are going to multiply on top and bottom by the reciprocal of what's causing our growth. So for us, that's going to be 1 over e to the 2x. Again, both top and bottom. So this is the limit. I guess this I can write equals. As x goes to plus infinity. Now, what do you have? Well, the e to the 2x's cancel, so you get 2 plus, what's the next term going to be? E to the x divided by e to the 2x. What does that become? Think of it as e to the negative x, or you can also think of it as 3 over e to the x. And then minus 5 over e to the 2x. Downstairs, similarly, you'll get 1 minus 4 over e to the x plus 3 over e to the 2x. Now, here's the great news. When we take this limit, well, the 2 is going to be a 2. 3 over e to the x? 0. 5 over e to the 2x? 0. Downstairs 1 is 1. 4 over e to the x? 0. 3 over e to the 2x? 0. Giving our final answer of 2. So here we actually have two horizontal asymptotes. So sometimes we write horizontal asymptotes by the y values. So negative 5/3 and positive 2. So there are two horizontal asymptotes. But that's only one type. We also have the vertical type. So when we're looking for vertical asymptotes, what are we looking for? Zeros in the denominators. All right, so e to the 2x minus 4e to the x plus 3 equals 0. We want to figure out when does that happen. So how can we figure that out? That looks complicated. Any ideas? Sorry, what? Factor? What? This is something you can factor? Well, turns out e to the 2x is e to the x squared. Ah. So it's almost like, let's say I'll call it capital Y. Y squared minus 4 capital, whoops. Okay, let's try that again. Y squared minus 4 capital Y plus 3. And if you saw that, you say, oh yeah, definitely that's a factoring thing. It's the same thing that you have here. Just we've changed it to a different name. So how does e to the x squared minus 4 e to the x plus 3 factor? E to the x minus 3 and e to the x minus 1. Aha! Even that technology was in such awe. Whoa. Let me take a minute to think about this one. Equals 0. All right, now, that says e to the x has to be 3, or e to the x has to be 1. Now, if I just wanted x, what would I put? How do I? Natural log. So, horizontal asymptotes would be log 3, and right, because log 3, oh, sorry, vertical. And the other one would be log 1, which is 0. Now, on a side note, could we have just used logs from the start? Where we just said, hey, e to the 2x minus 4 e to the x plus 3. Let's just go crazy and do a log here. Is that a good idea? And why is the answer no? It's not a good idea to use logs here, and the answer is logs do not work well with addition. Logs are absolutely atrocious. As soon as there's an addition in a log, the log just says, forget it, I'm out of here. I'm not going to work with addition. That's not my crowd. It wants multiplication. Logs love multiplication, but addition is kryptonite. Is this the answer? X equals log 3 and x equals 0. Because we found all the places where the denominator is 0. Now you're probably like, uh-oh. I know he wants me to say yes, but I know the answer has to be no. He wouldn't ask the question if the answer was yes. We found the places where the denominator is 0. If the denominator is 0, must you have a vertical asymptote? No. You don't have to have a vertical asymptote if the denominator is 0. If what's happening upstairs? You get a 0 upstairs. You might get some cancellation. Oh my gosh, which means we got to do what? We got to look at the upstairs. Let's look at that upstairs. Okay, let's see. Could we do anything with 2e to the 2x plus 3e to the x minus 5? Well, again, I can think of it as factoring. 2e to the x squared plus 3e to the x minus 5. And does this factor? What do you think? Does it? If it factors, what does it factor as? 2e to the x minus 5. I think it's plus 5. And e to the x minus 1. Let's check. 2e to the 2x minus 2e to the x plus 5e to the x would be plus 3 and minus 5. So actually, it turns out that our function is really 2e to the x plus 5 times e to the x minus 1 upstairs, and e to the x minus 3 times e to the x minus 1 downstairs. Those terms actually cancel. Now, they don't cancel, by the way, at x equals 0. The function is undefined at x equals 0 because you're going to get 0 over 0. But away from 0, we see it's actually a fairly reasonable function. So x equals 0 is actually not a vertical asymptote. So be careful, be careful. You have to check. Now that we're really paranoid, we might ask the question, uh-oh, what about log 3? Well, the answer is, look at what happens when you plug log 3 upstairs. E to the log 3 is 3. You get 2 times 3 plus 5 makes 11. If you have a number that's not 0 over something that's going to 0, that's an asymptote. So your vertical asymptote, there's just one. It's at log 3. So there are 3 asymptotes, 2 horizontal and 1 vertical. All right. Good. That's a fun one. Pay attention. Pay attention. Okay. Number 7. For the functions f of x and g of x, we have the following information about the tangent line. So in other words, we don't know the functions f and g, but we know a lot about the derivatives. Oh my goodness, a lot about the derivatives. More than we'd care to know, perhaps. Okay, so for instance, I can read off the chart. If I look at x equals 3, the tangent line at x equals 3 to g of x is 7 minus 2x. All right, so I have this information. And what we're going to do is we're going to find a bunch of tangent lines. Now, the way that this problem works is it's really testing the following. Do you understand the following principle? And if you can get the following in your mind, if you see a problem like this, it's not going to be hard. You're going to be like, I know how it works. And if you don't understand the following principle, you're just going to stare at the page for 74.5 minutes, only to have an epiphany in the last 30 seconds. That's a bad time to epiphanize. You want to have your epiphany before the test. Okay, so here's the idea. So if I have a tangent line to the function, say y equals h of x, at the point x equals a. So that's sort of, I'm saying I have that information. This is the exact same as saying the following. I know 2 things about my function h. And the 2 things I know about my function h are I know the value of the function at a, and I know the value of the derivative at a. I know those 2 things and only those 2 things about the function. No more, no less. Now the fact that I know the value of the function at a comes from the fact that the word tangent means we touch. It touches the line, so it has to agree. The derivative corresponds to the rate of change. It's the slope of the tangent line. So when you understand that, when we say we've given you a tangent line, what we've really done is said, hey, here's information about the value of the function and its derivative. Conversely, if I know the value of the function and the derivative, I can give you the tangent line. So if you can be comfortable about moving back and forth between these 2 pieces of information, this problem is going to be quick. And if you're not comfortable, well, we've got 4 chances for you to start warming up to it, because it's 4 parts. Our last multi-parter. So we're going to go through, we're going to find a bunch of these. Let's start with A. So here we have h of x is 3f of x minus 2g of x at x equals 4. So I want to find the derivative. Now what we're actually testing here as we go through is we're also testing on things such as product rule and chain rule and quotient rule. And these are all present here. So for instance, okay, that's part A. So we have h of x equals 3 f of x minus 2 g of x, and we're at x equals 4. So if I want the tangent line at 4, coming to my basic rule of thumb, that says I need h of 4 and I need h prime of 4. Because once I have that information, I get my tangent line. So I say, okay, let's start by finding h. h at 4. That would be 3 times f of 4 minus 2 times g of 4. So now I say, all right, I need f of 4. So I say, hey, wait a second. I have the tangent line to f at 4. So this tangent line contains information about the value of f at 4. How do I extract f of 4 from the tangent line? Plug it in. 3 plus 4, 3 plus 4 is 7. Minus 2. Now I want information about g at 4. We come over here. Plug in 4. 9 minus 12, negative 3. So we get 21 plus 6 makes 27. All right, that's the function at 4. Now I need h prime of 4. Well, if I'm going to find h prime of 4, I better find h prime of x. And here, this is a very simple product rule, not product rule, a sum rule and a constant multiple rule. So that's 3f prime of x minus 2g prime of x. So plug in 4. H prime of 4, that's 3 times f prime of 4 minus 2g prime of 4. And the information about f prime of 4, I go to the tangent to f of x at 4. F prime of 4 is 1. And g prime of 4? Negative 3. So we're going to get 3 plus 6, which is 9. And now that you have the value of the function and the value of the derivative, the tangent line is y minus the y value is equal to our slope, which is 9, times x minus the x value. And we're at x equals 4. Now, if you wanted to, you could clean this up. You could say that this is the same as y equals 9x. Let's see, this would be minus 36 plus 27. So that would be 9x. Why am I thinking so hard? Minus 36 plus 27 would be minus 9. Yes? That's the answer for part A. All right, like I said, the rest of these are going to be a very similar process. So once you understand it, it gets very simple, almost repetitive, but that's okay. It's good to repeat until we've got it down cold, so that if we see a problem like this, we'll be ready. All right, so for part B, h of x is now f of x squared times g of x squared. But here, the f, the x squared is on the inside. For g of x, the square is on the outside. And we're at x equals 2. So h of 2 would be f of 2 squared, which is 4, times g of 2 quantity squared. What is f at 4? Yeah, we already found it. That's 7. All right, what is g at 2? It's also 7. And then we square it. And this was a bigger number than I had intended. That turns out to be 343. If you had left it at 7 cubed, perfectly fine. Perfectly fine. Okay, now what do we need? We need h prime of 2. So we're going to get there by starting with h prime of x. So the derivative of f of x squared times g of x squared. So I start derivative of the first. Now somebody asked, what if I say, no, I like to do the function first times the derivative of the second, and then derivative of the first, and then the second. And the answer is, that's fine. We're not testing you on, do you know the rules as we state it? We're testing on, do you know the rules? And any way that does it works. So I like to do the derivative of the first. Okay, so f prime of x squared times 2x times g of x squared plus f of x squared times 2 g of x to the first times g prime of x. That would be the rule. If we apply the chain rule for the second one. Now what do? Plug in 2. So we're going to get f prime of 4 times 2, which is 4, times g of 2 squared plus f at 4 times 2 times g of 2 times g prime at 2. So f prime of 4. So come to our chart. F at 4. F prime of 4 is 1. G of 2. So g of 2, 7 squared. F at 4, 7 times 2 times g of 2, 7 times g prime of 2 is 1. All right, so you get 4 times 7 squared plus 2 times 7 squared, which is a number. indeed it is. 200 and, let's see, what would it be? 294. Now, you might be thinking, do I need to know 294? No. The numbers aren't going to, the numbers will be vetted. These numbers were not vetted. So, all right. So, okay, so now what do we do? After we've reached this stage, what's next? Well, yeah, we put the answer. We're ready, because we've gotten our information. See, we've gotten our value, the function value of the derivative, so we could say that y minus the y value is equal to our slope, 294, times x minus our x value, which, for some reason, I'm going to choose to leave like that. So, all right. Now, the others. Okay. So we're going to put some space here. A fresh sheet. All right. Actually, we'll do it this way. Here we go. Okay, so we're going to be able to do the rest. We'll do these a little bit faster. We just want to practice. Okay, so here we go. H of x, that's f of g of x plus x f of x. And we're at x equals 3. So we start, and we're going to start by plugging in, quiet. We're going to start by plugging in 3. So h at 3, that's f of g of 3 plus 3 times f of 3. In other words, everywhere where I see an x, I've put in a 3. And now we start working this out. Okay, g of 3, what is that? Well, g of 3 would be 1. So really this is asking what is f of 1. So we say, okay, f of 1 is 1. So we get 1 plus 3 times f at 3. Okay, f at 3, so we come here, f at 3 is 7. So we get 1 plus 21, which makes 22. H prime of x, that's f prime of g of x times g prime of x, chain rule, plus product rule, f of x plus x f prime of x. So we plug things in. So h prime at 3 would be f prime of g of 3 times g prime of 3 plus f at 3 plus 3 f prime at 3. So g of 3 we know is 1, because we did it just a minute ago. F prime at 1, negative 5. So we get negative 5. G prime at 3, negative 2. F at 3, 7. Plus 3 times f prime at 3, 2. So negative 5 times negative 2 is 10. Plus 7 gets us to 17. Plus 6 more gets us to 20 and 3. So with our information about h and h prime, now we go to our tangent line. So we get that our tangent line is y minus 22. Our y-coordinate is equal to our slope, 23, times x minus 3, which is our x-coordinate. And we'll leave it right there. All right. Last one for this one. Part D. Part D. So, what rule do you have to use for f of x plus 1 over g of x plus 1? Quotient rule. Good. Now, you might wonder, have we actually used all of our information? We actually haven't used the whole table. Do you have to use the whole table? No. And some of the problems that you'll see in the next few semesters, because why would you stop at Calc 1? You're going to see that we give you more than you need sometimes. So it's good to pay attention and say, look, what do I really need? What do I really need? All right. So h at 1 would be f of 2 over g of 1 plus 1. Well, f at 2, come to our table, f of 2, negative 2. G at 1, 6. And then plus 1 gives us negative 2/7. H prime of x, well, quotient rule, the bottom, g of x plus 1 times the root of the top, f prime of x plus 1 times 1, because I'm doing the chain rule, minus the top, f of x plus 1, times the root of the bottom, g prime of x, the plus 1 disappears, all over the bottom term squared. All right, I can move that up a little bit. So h prime at 1, well, that's going to be g of 1 plus 1, but we actually know what g of 1 plus 1 is. That's 7. Then we're going to times it by f prime of 2. F prime of 2, negative 3. So 7 times negative 3 minus f of 2, well, we already found that, that's negative 2, times g prime of 1. G prime of 1, 2. And then we're going to divide that by g of x plus 1 squared. Well, we actually know what g of x plus 1 is. Sorry, g of 1 plus 1 squared. That's going to be 7 squared. So we get minus 21. Then minus minus makes plus 4. So that ends up being negative 17 over 49. So the answer is going to be y minus our y coordinate, negative 2/7, is equal to our slope, minus 17 over 49, x minus our x coordinate, which is 1. All right, and there you go. So once you understand, I can go from tangent line to 2 pieces of information, and I can go from 2 pieces of information to tangent line. Problems like this are very quick and very simple. All right, next problem. You are a safety inspector for a roller coaster ride that is designed to go back and forth along a track that follows the curve y equals 1/4 x squared plus 4. So you have this sort of shallow parabola. So there's a little roller coaster that travels on this parabola. All right, so here's our little roller coaster, and it's moving back and forth. Now, as you're walking along under the track, you discover that there's a bolt over here. And this is located at the point 3, 0. So you've discovered a piece, and the piece came off the coaster. So that's what it's saying. You're walking on the track, there's a bolt, it's located at the point 3, 0. You believe that it came off the coaster as it was moving on the track and flew in a straight line to where it landed. Now notice the key here. It even italicized the word straight line as if to emphasize there's a straight line. Okay. Determine the point, or possibly points, that you should inspect on the track to make sure there's no other damage. In other words, the points where the bolt might have come off. Now you might say, okay, well, straight line, the roller coaster is moving, so what straight line is it? Well, we're looking for the straight line. That would be like this. So it's really talking here about a tangent line. Because the bolt, is when it comes off, it's going to stop moving on the track, and it's just going to say, I'm going to keep moving as I'm currently moving. Now, you might say, but what about gravity? It was moving very fast, so gravity had a negligible effect. It's a very fast coaster. It's very exciting. Okay. So how can we phrase this problem? Well, it's given to us as a story problem, but now we can rewrite it and say, hey, I want to find all tangent lines to the curve y equals 1/4 x squared plus 4 that pass through the point 3, 0. This is the actual problem. The rest of this is fluff. Now, you might say, how could I have figured that out? There's a couple of key words. For example, 3, 0. It's a number. Whenever you see a number like, I'm suspicious about the number. y equals 1/4 x squared plus 4. If you see a function, I'm suspicious about the function, and straight line. Those are like red flags saying, hey, here's how you should be thinking of it. There's this function, there's a point, and there's a straight line. And when you see a function, in this part of math, you should be like, when you see a line, you should be like, tangent line. All right, good. So we're sort of like the problem whisperers. You know, we want to like lean in and say, what is that? What's that? Oh, you want me to take a derivative? Oh, you naughty little problem. So, no, you don't have to say that. You don't have to say that. So, but, all right, we're going to listen. We're going to listen. Okay, so, what do we do? Well, we need to find a tangent line. So if we need a tangent line, what information do we need? Derivative, right? Okay, so what's y prime? 1/2 x. Yeah, and that's it. Okay, well that's great. That's the kind of derivative that you hope for. Okay, so now we have to find a tangent line. Now the thing is, there's many possible tangent lines. So we're going to just say, well, let's just imagine for right now, let's just call this A. A is unknown. That's where we're going to have the tangent line at. So our point, well, that would be A and then the value of the function at A. 1/4 a squared plus 4. The slope, well, that would be 1/2 a, because I plug A in. Now I have my line. At least I should say I have the data to make the line. So my line would be y minus the y coordinate, 1/4 a squared plus 4, is equal to my slope, 1/2 a, and then times x minus my x coordinate, which is a. Okay, so there's my tangent line. That's a generic tangent line. And oftentimes if you're asked to find a specific tangent line, you say, let me find all the tangent lines, and I'll pick out just the right one for me. So we've got our tangent line, and we say, I need to make sure my tangent line goes through 3, 0. How do I know if my tangent line goes through 3, 0? Yeah, you plug in 3 for x and 0 for y. That's how you know if it goes through 3, 0. Plug it in. So we need to have 0 minus 1/4 a squared plus 4 is equal to 1/2 a times 3 minus a. And now we have an equation just with a. That's lovely. It's our favorite type of equation because that means we can solve for a. So we start working this out. So let's see, that's minus 1/4 a squared minus 4 would equal, distribute the half a through, 3/2 a, then minus 1/2 a squared. Okay, that's so far nothing too crazy. What's the next thing we should do? Move everything to one side. This is polynomial. And the way you always do polynomials is you shove everything to one side and cross your fingers and say, please factor, please factor, please, 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 please. I've been a good calculus student. Okay, 1/2 a squared minus 1/4 a squared should give us 1/4 a squared, then minus 3/2 a, and minus 4 equals 0. All right, now before we factor, we should probably do something to help us keep our sanity. Get rid of fractions. Fractions, they have vexed us for far too long. Be gone, fractions. How do we get them rid of? Multiply everything by 4. That'll get rid of all the fractions. A squared minus 6a minus 16 equals 0. We're looking for two numbers that multiply to negative 16, and where you put them together, they'd add up to negative 6. Are there any two numbers which have that beautiful property? Yeah, 8 and 2. And so this is going to factor as a minus 8, a plus 2. So, what does that say about a? 8 and negative 2. Which means that there was actually another tangent line, because we can think of that as like, oh, this is like negative 2. But then there was this like tangent line way off there that we couldn't see. But, okay, so we have that there are two potential points. Now let's go back and make sure we answer the question. We want to make sure we give it the answer that they want. So it says determine the points that you should inspect. So our answer better be what? it better be points. Because remember, what do we want? Points. In this case, points from the problem, but we also want points on the exam. It has a double meaning. Is that a double entendre? No, I don't think so. Okay. All right. So, we know the x coordinates, -2, comma, and 8, comma. Now, how do we get the y coordinates? Because we need points. Plug them in to the original, because the function gives us the points. The derivative gives us the slope. -2 squared is 4. 4 times the fourth is 1. Plus 4 more, 5. 8 squared is 64. Times the fourth would be 16. Plus 4 more would be 20. And there are the 2 points we should go inspect. -2, 5, and 8, 20. On a side note, if you've ever been bored in an elevator and read the inspection signs, because of course, who doesn't do that when they're in an elevator? The people who inspect elevators in Iowa also inspect amusement park rides. So, I didn't say it was an interesting side note. Okay. So, using the limit definition of the derivative, find the derivative of f of x equals 3x squared plus 4x. Now, I said there'd be another one. And I said, okay, we're going to take a look at it. Again, really we should say a limit definition, because I said there was 2. So we talked about one. Let's talk about the other. F prime of x is the limit as z goes to x of f of z minus f of x over z minus x. So this is the one where it actually makes sense to say, oh, it's like that instantaneous rate of change. Because you see, this looks more like an average rate of change. And then you say, take the limit of the average rate of change, gives you your instantaneous rate of change. Now, you might say, but isn't the other one always better? Well, it just depends on the situation and the interpretation. So it's good to know both. If you have to just pick one for a computation, I would say the one with the h going to 0 is probably easier to work with. If you have to pick one for understanding, it depends on the problem that you're doing. So, if I want to take f prime of x, I'm going to use this variation just to see how it works. Limit as z goes to x of f of z minus f of x, and divide that by z minus x. So, you always write down the definition, get a couple points. Now here, it's kind of easier to figure out because you don't have that f of x plus h, it's just f of z. What do? Well, everywhere where you see an x, you put a z. 3z squared plus 4z. And I like to put parentheses just so I don't miss any minus signs. F of x, 3x squared plus 4x. And divide that by z minus x. Now, our goal is still the same. Our objective hasn't changed. We want to cancel off what's causing zeros. In this case, it's z minus x causing zeros. So I want to cancel off enough things so the z minus x's go away. So how do we do that? Well, in this case, what we do is we start by rearranging. So we can write this as 3 times z squared minus x squared. Then we have plus 4 times z minus x. And then we divide that by z minus x. For polynomials, it's fairly easy to rearrange. What can we do next?
Difference of squares.
Yeah, z squared minus x squared is the difference of squares. It's z minus x, z plus x. Whoops. And then plus 4 times z minus x, all over z minus x. And to make it really explicit, we'll go ahead and factor out the z minus x from upstairs. So z minus x times 3 times z plus x plus 4. All over z minus x. And here we see, aha, our cancellation has occurred because we're good people. We've lived a good, clean algebra life. And at this point now we can plug in. So what do? Well, remember we keep our limit notation until we're ready to take our limit. And now that we've done our cancellation, our limit just says everywhere where you see a z, put an x. So this becomes 3 times x plus 4, or 3 times 2x, also known as 6x plus 4. Now, what should you do to check?
Power rule.
Well, come back and check. What's the derivative of 3x squared plus 4x? That's one you can probably do in your head, I hope. It's 6x plus 4, right? So that's how you know you did it right. Now, I will tell you, when we grade these problems, there were a lot of people who will get to an answer that's not 6x plus 4, and they'll just be like, okay, whatever, I don't need to check. That's a dangerous strategy. You should always check. Now, there are other people who are like, I'm just going to write down a bunch of stuff over here, and then miraculously I'm going to get 6x plus 4, because they don't check this, right? No. They check this. They look closely. They pull out their scanning electron microscopes, making sure you have the limit in every single place there's supposed to be a limit. Don't underestimate our ability to find an error. We're really good at it. Okay, number 10. Determine constants a, b, c, d. Ooh, we get to find 4 different numbers. So that the function is continuous at -1 and differentiable at +1. All right, so let's just work from the left to the right. So, continuous. To be continuous, the key is that the limits from the two sides have to agree. So, what we need to do, let's work at continuous at -1. We'll start over here. Continuous at -1. So we need to have that the limit as x approaches -1 from below of g of x has to equal the limit as x approaches -1 from above of g of x. Now, one of these limits is easier than the other one. For instance, the limit as x approaches -1 from above, well, when I'm just above g of x, what does my function look like? Sorry, when I'm just above -1, what do I look like? I look like the middle part, just above -1. So this would be just this number b, and the limit of the value b is b. Okay, so we now know that b is going to be whatever this limit is. All right, so we just have to find this limit. So let's see, we get x squared. Oh, don't forget to write down the word limit. Limit as x approaches -1 from below. X squared plus ax plus 7 over x squared plus 4x plus 3. So the first thing we always do when we try a limit is to do what? We plug in. And we just say, all right, maybe they made it really nice on us. Okay. What do we get? Downstairs? Oh, let's do upstairs first. -1 squared is 1. And then we have minus a and plus 7. And downstairs we get -1 squared is 1 again, minus 4 plus 3, which becomes 8 minus a over 0. Okay, so we now know that b is, wait a second, hold on. Uh-oh. We have a 0 downstairs. But we need to have the limit exist. There has to be something. Uh-oh. What does that tell us?
More work.
A has to be 8. So this has to be 0 or limit can't exist. And we know the limit exists. And so our conclusion is, let's put our list of values over here. A has to equal 8. Nice. Okay, so now we're going to 0 over 0. All right, now let's update our limit. So really, we have the limit as x goes to -1 from below. It's going to be x squared plus 8x plus 7 over x squared plus 4x plus 3. And we already know it's going to 0 over 0 because we chose it to make sure we had a 0 over 0 going on. So if we know it's going to 0 over 0, we know in our heart of hearts what must be true. That it's going to factor, and what else will happen? That there's going to be some cancellation. Okay, we know it's going to factor because we know that -1 are roots. And because we know -1 are roots, it actually makes it factoring super fast. Because that says that x plus 1 has to be a root of the upstairs and has to be a root of the downstairs. What's left upstairs? X plus 7. What's left downstairs? X plus 3. The x plus 1's cancel. Now we take our limit. What do we end up with? Well, negative 1 plus 7 upstairs. Downstairs, negative 1 plus 3. Known as 6 over 2 or 3. So, and remember, what is that? That's the limit. That's our b. So we've just found b. b is equal to 3. Now we continue on. We've saddled on continuity. Differentiable. Now differentiable says what? Well, differentiable says the following. The functions on both sides match, but that's just continuity. So to be differentiable, you have to be continuous. That's an important fact. Differentiable, you have to be continuous. Is this enough? It's not. What else has to match? The slopes have to match. Or in other words, the derivatives. Derivatives. Okay, we'll abbreviate that. The derivatives have to match. All right, good. Okay. So our functions have to match and our derivatives have to match. Now that actually makes life easy because we know what b is. See, b is 3. So we know in particular we need the limit as x approaches 1 from below of 3, which is 3, has to equal the limit as x approaches 1 from above of e to the c to the x minus 1 plus d times x. Well, let's plug in 1. Because this is a nice continuous function. When you plug in 1, you get e to what power? 0. E to the 0 is 1 plus d times 1, which becomes d. So 3 has to equal 1 plus d. So what can we say about d? d is 2. All right, we've gone 3 of our 4 numbers. But that's just a function. The derivatives have to match. So we do the derivatives. Limit as x approaches 1 from below. What's the derivative of 3? 0. What's that limit?
0.
0. That's right. The limit of 0 is 0. That has to equal... Whoop, why did this become a... Yeah, that's right. Limit as x approaches 1 from above. Yes. Okay, good. What's the derivative of e to the power c times x minus 1? It's c e to the c to the x minus 1. What rule is that? Chain rule. Chain rule. Chain rule. Okay, derivative of d times x is d, but we actually know what d is, because we can come up here and actually update it now. So, plus 2. So, let's take this limit. What do we get? I'll do the plus 2 part. C. And then you get e to the 0, which is 1. So 0 has to equal c plus 2. So what is c? Negative 2. And that's it. We found our values. 8, 3, negative 2, and positive 2. Which brings us to our last problem. So, reviewing reports on the efficiency of an air purification system, which takes as input peanuts, which we'll denote as P, you see that the number of cubic centimeters of air purified is given by the function. And there's this function here. It does something. Okay, whatever. You note that someone has boxed a value which reads 240 centimeters cubed over peanuts squared. But there's no other context. To help figure out what this might mean, find the input P that could produce this result. So there's some P that is somehow connected to this measurement here. Now, you might wonder, why peanuts? Well, this is Carver Hall, named after George Washington Carver, who was a student at Iowa State, and also liked peanuts. All right. So, who knows what we're going to have in the future? You know, another fun fact, well, okay, maybe I'll just say another fact. You might not think it's fun. Is that the person who invented Rice Krispie treats was also a student at Iowa State. Does that mean we're going to have a problem about Rice Krispie treats? Who knows? Who knows? Someday I hope to. All right. It's on my list of problems to put on before I retire. So, let's think about what this is. So, 240 centimeters cubed over peanuts squared. Now, the way that we would read such a number here is we would say centimeters cubed per peanut squared. That's how we'd oftentimes read units. But here's the key idea, is that units are important. So units tell us something. Whenever you see a fraction going on, that means there's a kind of rate. So this is really a unit that involves a derivative. So there's some derivative going on. Now here's the question. Which derivative happened here? So we see a 3. We see a 2. Maybe we should average and say there were 2.5 derivatives. No, we don't do that. We don't do that. So the question is, what's the right answer? Someone has said second. Why do you think second? Because of where the units are. See, the cubed here, you get that because that's the units of your function. That's where those units are coming from. And in general, if you remember how this works, if I'm taking let's say, a derivative, the nth derivative of y with respect to x, the units of this become, it's whatever units of y you have over the units of x to the nth power. So whenever you have to deal with units, you just remember it's, okay, whatever my output units are, in this case it's centimeters cubed, over whatever my input units are to whichever power derivative I took. So because I took a second derivative, I would have peanuts squared because my input is peanuts. So this is a second derivative. Okay, so we're dealing with the second derivative. So we say, aha, this piece of information told us that there's some p where f double prime of p is equal to 240. So to figure out the p means to solve this equation. So if I'm going to figure out when does f double prime of p equal 240, we should probably find f double prime of p. And if we're going to find f double prime of p, we should probably find f prime of p. And we already have f of p, so look, I just found that, so that was quick. F prime of p. Derivative of negative p to the fourth? Negative 4p cubed. Derivative of 6p cubed? 18p squared. 180p squared? 360p. Minus 70p? Minus 70. Derivative of e to the 20? E to the 20, right? Because it's like, oh, wait, 0? What? Oh, there's no p there. It's a constant. Okay, all right. Yeah, right, good. Pi to the 23rd. Bring the 23rd down, pi to the 22, yes? No. It's a constant. Oh, my goodness. Yeah, pay attention. Okay, f double prime of p. What is that? Negative 12p squared plus 36p plus 360, and the 70 goes away. In fact, we kind of knew ahead of time that these terms on the end were going to disappear. The constants, yes. This one, because it's to the first power, after two derivatives, that would be gone. So, we're almost done because we have f double prime. We set it to 240. Now, we start moving stuff around. Minus 12p squared plus 36p plus 120 equals 0, because I'll bring the 240 across. Now this looks a little bit hard to work with. We know it's a polynomial, but I don't want to try to factor yet because that negative 12 just doesn't feel right. So let's get rid of the negative 12. So we'll divide everything by negative 12. So that would give us just p squared, like, that feels a lot better. 36 divided by negative 12? Negative 3. 120 divided by negative 12? Negative 10. Now, does p squared minus 3p minus 10 factor? Yes. How does it work? P minus 5 and p plus 2. Which means that we get one of two possibilities. 5 units of the peanuts or negative 2 units of peanuts. However, it's unlikely that we can somehow create -2 peanuts. I mean, if a peanut and an anti-peanut meets, and is that how you make peanut butter? No, no. So the answer is 5. 5 was what this measurement corresponds to. All right, good. That's it.